Page 55, the IUPAC nomenclature of alkanes. I found this page to be difficult for students, and so I rewrote the same rules using simpler examples on page 56. So we'll start with 56. You can go back and do page 55 after 56. IUPAC names are made of three parts. There's the parent name, which states how many carbons are in the longest chain. Bute for 4, pent for 5, hex for 6. Then the suffix at the end is the family. For example, ane is alkane, ene for alkene, ine for alkyne. And then the prefix lists the substituents that are present. So to begin with, we find the parent hydrocarbon. That is, we find the longest chain of carbon atoms and assign the parent name to it. In this example, the longest carbon chain, remember to count any direction at all. I see 6 carbons is the longest carbon chain. So the parent name and the suffix will be hexane. Let's go to the second example. We'll come back to finish this after. If 2 chains in a molecule are the same length, choose the chain with the greatest number of branch points. So take a look at this example. I could number it this way: 1, 2, 3, 4, 5, 6, 7. Or I could number it as 1, 2, 3, 4, 5, 6, 7. Choosing the first route gives me more branch points. I have a branch here, and here, and here. If I come straight across, I only have 2 branch points. So we're going to choose that winding road in blue. So doing that, we have 7 carbons in the main chain. Therefore, this is going to be heptane. Number the atoms in the main chain, beginning at the end nearest the first branch point. Alternate numbering patterns are compared. Choose the one that gives the lowest number at the first point of difference. If there's a tie, use alphabetic priority to decide between equivalent numbering patterns. So go back to the first one here. We have a methyl group on this carbon and this carbon. So if I number from left to right as I have, I'd have a methyl substituent on the 3rd and 5th carbon. If, however, I number it this way, 1, 2, 3, 4, 5, and 6, then I have methyl groups on the 2nd and 4th carbon. So we're going to choose the direction that gives the lowest locant number for the first branch point, so the one in green. So I would name this as, this is a 2 methyl group, and I have a 4 methyl group. So put this all together in one name. This will be 2, 4 hyphen dimethyl hexane. So be sure to separate numbers from numbers with commas and numbers from letters with a hyphen. Do you have to say di? Yes, you do. All right, let's try the next one. I'm looking for the direction that gives me the lowest locant at the first branch point. That would be, I better use a different color. Let's go 1, 2, 3, 4, 5, 6, and 7. So if I number in red here, my first branch point is on the 2nd carbon. So that'll be my direction of numbering. Let's list the substituents from that. I have a methyl group on the 2nd carbon, so I'll say 2 methyl. I have an ethyl group on the third carbon. I'll say 3-ethyl, and I also have a methyl group on the third carbon as well, so that's 3-methyl. Now I'm going to list these together, and the substituents are listed alphabetically, not numerically. So E in ethyl comes before M in methyl, so the 3-ethyl is listed first. This will be 3-ethyl hyphen 2,3 dimethyl heptane. It's one word with no spaces, separating numbers from letters with hyphens, separating letters from letters with commas, and use a prefix when there's more than one of a particular substituent. In rule number 4, use prefixes di, tri, tetra, etc. when more than one substituent is the same. These prefixes are added unhyphenated, and they are not used for alphabetizing. Notice up here, the D in di actually alphabetically would come before ethyl if it was alphabetized, but the prefixes are not alphabetized, so the E in ethyl becomes before the M in methyl. Let's try the next one. Find the longest carbon chain. 1, 2, 3, 4, 5, 6. No difference if I go 5, 6. So go in any direction, find the longest carbon chain. It looks like it's going to be hexane. If I start numbering from the right, my first substituent is on the third carbon. If I number from the left-hand side, I'll do this in green. Let's say 1, 2, 3, 4, 5, 6. In this case, my first substituent's also on the third carbon, so it makes no difference whether I number left to right or right to left. Now the substituent here is an ethyl group, and here is a methyl group. So E comes before M, so I'm going to number it from left to right. So it'll be 3-ethyl 4-methyl if I number it from left to right. Had I numbered it from right to left, I would have had 3-methyl 4-ethyl. So we compare alternate systems. When there's a tie, the alphabetization prioritizes E before M. So the name of this compound, therefore, is 3-ethyl. Substituents are listed alphabetically, not numerically. 4-methyl hexane. Very logical. Now there's one additional rule here, rule number 5, for complex substituents. I'll explain what they are in a second. They're named using the 4 previous rules, except that the number 1 carbon in the branch is the head carbon. That's the point of attachment to the main chain. To avoid confusion, complex substituents names are put in parentheses. We'll need to look at page 57 to see this. So this compound, the longest carbon chain, I'll number left to right, 1, 2, 3, 4, 5, 6, 7. Doesn't matter whether I go left to right or right to left. The longest carbon chain is 7. This is going to be heptane. There's a substituent on the 4th carbon. So what is it? Well, if we use the common system, this is the head carbon. It's the carbon bond to the main chain, and it's a 3-carbon group, so it's a propyl group. Now you can see it's not N-propyl. It's not a straight chain. It's a branch chain. Second from the end is a methyl group. Can you see that this is an isopropyl group? So I can describe this as 4 isopropyl group on the 4th carbon. Now let me put this together. This would be 4 isopropyl heptane. No spaces. Now you say, well, this is a common name connected with an IUPAC name. That's correct. The IUPAC system accepts the common alkyl group names. Now if you're a purist, if you want to use the pure IUPAC system, what is the name of this alkyl group? Well, this would be 1, 2. The longest carbon chain, starting from the head carbon, is 2 carbons. This would therefore be a 1-methyl-ethyl group. And so I can also write this as 4 as the location on the main chain, hyphen bracket, 1-methyl-ethyl, close bracket, heptane. This is pure IUPAC. I've used an IUPAC alkyl group name. Now, when you use a complex name like this, you need to put it in parentheses to avoid confusion, to show that it's all together in the same alkyl group. You will find that whenever possible, you will use the common system rather than a strictly IUPAC system, if possible. Let's check the last example here. Let's find the longest carbon chain. I'm just going to try this way. 3, 4, 5, 6, 7, 8, and 9. Pretty sure that's the longest chain. That'll be nonane. Now, which direction do I number from? If I number from the top, my first substituent's on the 3rd carbon and the second is on the 4th. If I number from the bottom, it would be first substituent on the 3rd, but the next substituent's not till about the 6th carbon, so I must number from the top. So numbering from the top, list my alkyl groups. There's 3 methyl, 4 ethyl, and 7 methyl. So putting this all together, alphabetically, E comes before M, so this will be 4 ethyl hyphen 3,7 dimethyl nonane. Logical just takes care. Let's go back to page 55. I want to point one thing out to you here that I didn't stress so far. Note that non-hyphenated prefixes such as cyclo, neo, and iso, they are alphabetized. You would consider the C, the N, the I in the alphabetization. But hyphenated prefixes like tert and sec will not be alphabetized. But prefixes di, tri, tetra are neither hyphenated nor alphabetized. Confusing? Perhaps. Try a few examples. It's not so bad. On pages 58, 59, and 60 in your course notes, there's an alkane naming exercise. And you can print out these pages and write the answers if you wish, and or on Blackboard there is an ACD ChemSketch file called alkane naming exercise.sk2. ChemSketch is chemistry drawing software that is free to students to download from the ACD ChemSketch website. And the hyperlink for this is in the syllabus in the course info section of Blackboard. Here's what that exercise looks like in ChemSketch. So there are 3 pages, and you can navigate between pages using the icon at the bottom that says page here. If you can't see that, up here at the top menu under pages, you can go to next page or previous page and such. You'll notice that some of these structures have boxes around them. So that's because I've covered the answers for the names to these structures. So you can reveal the names a couple of ways. You can click on the large outer box and then left click on the fill color to make it no fill color and reveal the locant numbers for the structures. Or you can simply move the box over to see the locant numbers. Also, the names are covered under the yellow box. You can do the same thing. Left click it to select it and then choose the no fill color. Alternately, you can simply select the structure itself and click on this button, which is the generate name for structure, and it generates the name for you. Now I have to warn you that in organic chemistry there are actually 3 systems of naming organic compounds in use. One is the common system, the IUPAC system, and the third is called the Chem Abstract system. And ChemSketch will seemingly randomly choose between any 3. So as you do this exercise, all of these examples will generate names in the systems that we are familiar with, the common and IUPAC. But if you choose to explore and draw other structures and ask for names, you may find there are some names that you're not familiar with, and that could very well be because it's choosing the Chem Abstract system. I should not forget to remind you that in ChemSketch, make sure that you are in the draw mode and choose the selection tool in the far top left corner. Now some of the structures I don't have boxes hidden, so you can just select them and reveal the names after you've worked it out yourself. Enjoy. We're going to do page 61 again, but this time using IUPAC names instead of common names to name these substituted cyclohexane compounds. We'll work from the top. The IUPAC name for methyl cyclohexane is methyl cyclohexane. No difference. Likewise for ethyl cyclohexane, it's the same in both systems. For N-propyl cyclohexane, this first example, straight chain, we'll just call it the same thing again, just propyl. You wouldn't use N in the IUPAC system, simply propyl cyclohexane. You have the option of using it in the common system, but it doesn't make any sense in the IUPAC system. But what will we call isopropyl cyclohexane? What is this in the IUPAC system? In the IUPAC system, we find the longest carbon chain counting from the head carbon. That's 2 carbons, so it's an ethyl group with a methyl group substituent on the first carbon. So that's going to be called 1-methyl ethyl. And that is a complex substituent, so it must be put in brackets. 1-methyl ethyl. Notice there's no spaces. Cyclohexane. Isopropyl cyclohexane is the same as 1-methyl ethyl cyclohexane. In rings, if there's only one substituent on the ring, it's understood to be the carbon 1, so it's not stated in the name. If there were more than one substituent, we'd have to state the locant on the ring. You might have like 1-methyl 2-ethyl cyclohexane. But in this case, since there's only one substituent, you don't use the locant number for the ring. It's understood to be only one position. Okay, let's move on. We got butyl cyclohexane in the common system. In the IUPAC system, that'll be the very same thing. It's simply butyl cyclohexane. Now what about isobutyl cyclohexane? In the IUPAC system, the head carbon is here. The longest chain from it is 3 carbons, so it's propyl with a methyl substituent on the second carbon. Remember, this is carbon number 1 by definition. The head carbon is number 1. So we have a 2-methyl propyl substituent. It's complex. We'll put it in parentheses. 2-methyl propyl. Cyclohexane. As you're writing these IUPAC names, count up the carbons. You know that there must be 4 carbons in total in the alkyl group because it's butyl. So here we have propyl is 3 and methyl is 1. The combination is 4. Just keep checking. I find that's a common error among students first learning this. What about T-butyl cyclohexane? What's the IUPAC name? This is carbon 1. The longest carbon chain is 2. So on carbon 1 we have two methyl groups. This would be 1,1-dimethyl-ethyl in brackets. 1, 1 dimethyl ethyl cyclohexane. And finally we have sec-butyl cyclohexane. Head carbon is here. Longest carbon chain is 1, 2, 3. There's a methyl group on the first carbon. This would be a 1-methylpropyl cyclohexane. Notice again, propyl is 3 and methyl is 1. That's 4 carbons, so it's some type of butyl cyclohexane. Pentyl cyclohexane in IUPAC is called pentyl cyclohexane. Okay, how about isopentyl cyclohexane? Head carbon is here. Count the number of chains, count the number of carbons in the longest chain. I count 1, 2, 3, 4. So it's going to be butyl with a methyl group on the third carbon. Looks like 3-methyl-butyl. Methyl-butyl cyclohexane. 3 and 1, 4 plus 1 is 5. A 5-carbon alkyl group. Neopentyl cyclohexane. Head carbon is here. 3 carbons in the longest chain. It'll be propyl with 2 methyls on the second carbon. So it's going to be 2,2-dimethylpropyl. 2,2-dimethylpropyl cyclohexane. And finally we have tertpentyl cyclohexane. This is the head carbon. 3 carbons in the longest chain. 2 methyl groups on the first carbon. Looks like 1,1-dimethylpropyl. Cyclohexane. 3 plus 2 makes 5. And now we have the 6-carbon alkyl groups. N-hexyl, or hexyl, is the same in IUPAC. Hexyl cyclohexane. We have isohexyl cyclohexane. The head carbon is carbon 1, 2, 3, 4, 5 carbons in the longest chain with a methyl group on the fourth carbon. Looks like 4-methylpentyl. 4-methylpentyl cyclohexane. 5 plus 1 makes 6 carbons. And finally we have neohexyl cyclohexane. The head carbon is here. Count 1, 2, 3, 4. So it's going to be a butyl group with 2 methyls on the third carbon. Looks like 3,3-dimethylbutyl. 3,3-dimethylbutyl cyclohexane. So remember, complex substituent names where there's 2 alkyl groups in the same group, you need to put in parentheses to avoid confusion. Now, just want to point out that these are not all of the isomers of the hexanes. I want to point out that these are not all the isomers of hexyl cyclohexane. I've only listed the ones that have common names, and there aren't common names for all the hexyl cyclohexanes. Again, the common alkyl group names only go up to 6 carbons, and they're not systematic. They don't cover all cases. Page 62, nomenclature of alkyl halides, also called haloalkanes. So alkyl halides are named like alkanes in that the longest carbon chain is the parent chain, irrespective of the position of any halogens. So halogens have no special status. Halogen substituents are treated just the same as if they were alkyl substituents. That is, they are numbered and listed alphabetically along with any alkyl substituents. There are 2 systems of nomenclature in use, the IUPAC and the common system. So in IUPAC, the halogen substituents are named as prefixes, haloalkanes, attached to the parent name. And the prefixes are fluoro, chloro, bromo, and iodo. And the position on the chain is identified by listing the locant number, or the number of the carbon to which it is attached. The name is given as one word with no spaces. They literally are named haloalkanes. So in this first example, this will be 1-iodopropane, and this will be 2-bromobutane. In this longer molecule here, we're going to have to number the carbons. That's carbon 1, 2, 3, 4, 5, 6. It's going to be hexane. We'll have substituents 1,1-dibromo. Then we'll have a methyl on the third and a fluoro on the fourth. So alphabetically that would be 1,1-dibromo, 4-fluoro, 3-methyl hexane. Very straightforward. In the common system, alkyl halides are named as alkyl space halides. 2 words. The alkyl substituent is named first, followed by the halogen named as if it was an anion, fluoride, chloride, bromide, or iodide. So here we have N-propyl, which is unbranched iodide. Here we have sec-butyl space bromide. And of course for this third one, well, there's no common name because common names have limited breadth. Multiple substituents on the same carbon have some special common names. We've already seen methyl, and if we have 2 single bonds on the same carbon, this is a methylene group. We've used that a few times. If we have 3 single bonds, 3 replacements of hydrogen on a single carbon, it's referred to as a methine group. It's not used much in nomenclature, but more in spectroscopy or identifying parts of an organic molecule. Ethane, minus 1 hydrogen, we know is called ethyl group. If there are 2 replacements of hydrogen on ethane and they're on the separate carbons, it's called an ethylene group. And if we have 3 replacements of hydrogen on an ethyl group but they're on the same carbon, it's called an ethyne group. This is less common, it's a bit obscure, but I put it here for sake of completion. When methane is chlorinated in the presence of ultraviolet light, a mixture of chlorinated methanes result, and industrially that's actually how these products are made. Many of them have common names as well as IUPAC names, and they're very common chemicals. So here's methane and chlorine in UV light, and there's a variety of substitution products that occur. You need to learn these names. So this will be chloromethane. Now this is a IUPAC, it's simply haloalkane, chloromethane. In the common name, recall it's alkyl halide. So this will be, the alkyl group is methyl space halide, methyl chloride. In IUPAC, this is dichloromethane. Common system, we call it methylene chloride. So the CH2 with 2 single bonds is called a methylene group. We use this solvent a lot in the labs. It has low toxicity. We use it for many organic reactions. Very common dichloromethane, aka methylene chloride. In IUPAC, this will be trichloromethane. The common name for this is chloroform. CCl4 would be tetrachloromethane. Common name is carbon tetrachloride. Carbon tetrachloride was, for many years, the solvent for dry cleaning fluids, but recently has been replaced. This will be dibromomethane, or methylene bromide, analogous to methylene chloride, CH2Cl2. CHBr3 would be tribromomethane, and so that would be called bromoform, analogous to CHCl3, which was chloroform. CHI3 is triiodomethane, and of course that would be iodoform, analogous to bromoform and chloroform. CH3, CHCl2 would be 1,1-dichloroethane, and that has no common name. I wanted to include it here because these two are commonly confused. This is CH2Cl, CH2Cl. The chlorines are on separate carbons rather than the same one. This would be 1,2-dichloroethane, and this does have a common name. It's ethylene chloride. And finally, CH2I, CHI2 would be 1,1,2-triiodoethane, and it has no common name. I created some images here in Know-It-All just to help us learn these. This is methyl chloride, aka chloromethane, and dichloromethane. The chlorine is green. Chlorine's a green gas. Dichloromethane is methylene chloride. Trichloromethane is chloroform, and tetrachloromethane is carbon tetrachloride. And here we have chloroethane, which is called ethyl chloride, or 1,2-dichloroethane, which has a common name, ethylene chloride. On pages 63 and 64 is an exercise for you to name alkyl halides. Now the answers are on Blackboard, but I'll do a couple with you right now. Let's try these here. So in the common system we name alkyl space halides. So I name the alkyl group. This is a sec-butyl group. This will be sec-butyl space fluoride. The alkyl group in this case is also a butyl group. This is isobutyl space bromide. Here's another butyl group. This is a T-butyl group. And finally, this is an N-butyl group. You can write N, or you can leave the N out and just say butyl iodide. So literally, alkyl space halide. In the IUPAC system, they're named as haloalkanes as a single word. So we'll number this. Carbon 1, 2, 3, 4. The longest chain is butane with a fluorine on the second carbon, so this is 2. Fluoro butane. Notice the difference in the endings. In a IUPAC it's halo. In the common system they're halides. We'll number this carbon 1, starting at the end closest to the first substituent, 2, 3. This will be propane, therefore, and it'll be called 1 bromo 2 methyl propane. Notice propane stands for 3 carbons, methyl for 1. 3 plus 1 is 4. In the common system, you name all the carbons collectively. Be careful on this one. Find the longest carbon chain. Don't always look horizontally. Let's look vertically. This is carbon 1, 2, 3. The longest carbon chain is 3 carbons. This will be 2 chloro, 2 methyl propane, and finally this will be 1 iodo butane. So I'll leave the rest of these for you to do and check your answers on Blackboard, and as I mentioned here, if you wish you could copy and paste them into ChemSketch and have the name generator give you the answers as well. On page 65 we have some practice, more practice with the IUPAC system. Let's name these chlorides. So the N-propyl chloride would simply be 1 chloro propane, and isopropyl chloride would be 2 chloro propane. N-butyl chloride would be 1 chloro butane, and sec-butyl chloride would be 2 chloro butane. Isobutyl chloride, the longest carbon chain is 3 carbons, so it's going to be a propane. That'll be 1 chloro, 2 methyl propane. And T-butyl chloride, longest carbon chain, look vertically, is 3 carbons, so it'll be propane. So we'll have 2 chloro, 2 methyl propane. Okay, the 5 carbon alkyl chlorides, this of course will be 1 chloro pentane, and this would be 2 chloro pentane. Notice this is one of the isomers that does not have a common name. The next one here is 3 chloro pentane. Isopentyl or isoamyl chloride. This is carbon 1, 2, 3, 4. This will be 1 chloro, 3 methyl butane. Tertpentyl or tertamyl chloride, longest carbon chain is 1, 2, 3, 4. That'll be 2 chloro, 2 methyl butane. This next alkyl chloride does not have a common name. We'll number it from the end that gives the chloride precedence because it'll be 2 chloro or 2 methyl. So we're going to number from right to left. 1, 2, 3, 4. Chlorine has alphabetic priority over methyl. This will be 2 chloro, 3 methyl butane. That is 1, 2, 3, 4. That is 1 chloro, 2 methyl butane. And finally, neopentyl or neoamyl chloride. Longest carbon chain is 3. Whether we look vertically or horizontally, it's 3. So that'll be 1 chloro, 2 dimethyl propane. And I'm going to count here. Propane is worth 3. 2 methyls is worth 2 more, total of 5 carbons, so it's some type of pentyl group. Good idea to keep track of that as you do these. All right, the last group, the 6 carbon alkyl chlorides. This would obviously be 1 chlorohexane, numbered from the end closest to the first substituent. Pentane, so it'll be 1 chloro-4-methyl pentane. Neohexyl chloride, carbon 1, 2, 3, 4. Looks like 1 chloro, 3 dimethyl butane. 4 plus 2 makes 6, 5 plus 1 makes 6, and 6. So that's it. Little practice. It's not too difficult, just takes some care. Page 66, the physical properties of alkanes. There's not a lot to tell. They're chemically unreactive to many other chemicals because they have strong nonpolar bonds. Now the typical bond strength of homolytic dissociation energy, D, in kcals per mole, for a carbon-to-carbon bond is about 85 kcals per mole, and a carbon-to-hydrogen bond is 100 kcals per mole. That may not mean anything to you, but as far as covalent bonds go, that's relatively high. Those are strong bonds. Alkanes have weak intermolecular forces. Those are the forces that hold separate molecules together as a liquid or a solid. They only have induced dipoles between individual molecules because they're nonpolar. And these are called London dispersion forces. They are the weakest type of van der Waals forces. And thus alkanes have very low melting and boiling points. It doesn't take much energy to separate solid molecules into the liquid phase or separate liquid molecules into the gaseous phase because they have weak intermolecular attraction compared to more polar compounds of similar molecular weight. So here I have water and methane. Their molecular weights are similar, but notice the melting point and the boiling point of water are considerably higher than that of the hydrocarbon because there's much greater intermolecular attraction between polar water molecules than compared to attraction between hydrocarbon molecules. Note, however, that melting point and boiling point increase with molecular weight because as the chain length increases, so does the surface area of each molecule, and thus the intermolecular attraction between each molecule has to increase. As a result, we see that the carbon 1 to carbon 4 alkanes, that'd be methane to butane, well, they're gases at room temperature. From C5 to C30, these alkanes are liquids at room temperature. Much above C40, and these are solids like waxes. Now, the divisions are somewhat vague here. They're not sharp because remember, hydrocarbons exist in many different isomeric forms, and those affect the melting and boiling points. So melting and boiling points decrease slightly as branching increases, because branched molecules have less intermolecular attraction. Take a look at this example. Here are 3 isomers of pentane. They're all C5H12. On the left we have N-pentane, straight chain, long stretched out molecule. Isopentane has 1 branch, a little bit shorter, and then neopentane, well, it's almost like a ball. So the surface area in N-pentane is the greatest per molecule, and neopentane would have the least surface area, and as a result, the boiling point of neopentane 10 degrees C is significantly less than the boiling point of N-pentane, where the molecules are stretched out. Note that alkanes are insoluble in polar solvents like water, but soluble in nonpolar solvents like gasoline and ethers, and the rule like dissolves like applies. Note that alkane densities increase with molecular weight. So here is octane, gasoline, density is 0.7 grams per mil. It floats on water. Perhaps you've seen gasoline spills on water. Hexadecane, density increases a bit to 0.77 grams per mil. Triocontane, density is a little higher, 0.81 grams per mil. And in the extreme case, let's look at polyethylene. 100,000 carbons long, the average chain length, density is increased to 0.95. But in all cases, all alkanes float in water. Even waxes in high molecular weight polyethylene float in water. Page 67, the reactions of alkanes. Not too much to tell because they're fairly unreactive. We'll look at combustion, halogenation, and pyrolysis. Certainly the most familiar reaction of alkanes is that of combustion. Alkanes are fuels. Our bodies burn fats, which are hydrocarbons, to obtain energy. Automobiles burn gasoline, hydrocarbons, for energy. And as you know, alkanes react exothermically with oxygen when ignited. Now, alkanes are hydrocarbons. When hydrogen is burned completely, it goes to water. When carbon is burned completely, it goes to CO2. So let's balance these equations. Here's butane with oxygen. As you no doubt know, leave the simplest compound to the end because putting a coefficient in front of oxygen affects only oxygen. Start with the more complex structures. So butane C4H10, I'll need 4 carbons on the right. I have 10 carbons on the left. Let's put a 5 here, and that's 10. So carbon and hydrogen are balanced. For oxygen, I now have 8 plus 5 is 13 oxygens on the right. I'll need 13 oxygens on the left. I have O2, so let's put 13 over 2, and 13 over 2 times 2 is 13, so it's balanced. But as you know, we don't use fractional coefficients, so if I multiply all the terms by 2, that'll maintain the equality of both sides, yet get rid of the fractional coefficient. So that's 2 C4H10 plus 13O2 goes to 8 CO2 plus 10 H2O. Here's octane, automobile fuel. C8H18, this will balance the carbon. 9H2O balance the hydrogens. That's 16 oxygens plus 9 oxygens is 25 oxygens on the right. I'll need 25 on the left. So again, I'll use a fractional coefficient, 25 over 2. 25 over 2 times 2 is 25. That should work. Then get rid of the fraction by multiplying by 2. 2C8H18 plus 25 over 2 times 2 is 25O2. 2 times 8 is 16 CO2. 9 times 2 is 18 H2O. And that's it. There are no mechanisms to learn for redox reactions because electrons travel every which way. Pretty random. We just can write balanced equations for the products. A second important industrial reaction of hydrocarbons is halogenation. And halogens will react with alkanes, replacing hydrogens, via a free radical mechanism. And what's a free radical? Well, it's a single unpaired electron on an atom. So ultraviolet light, UV, often written as h nu, the energy of a photon, is energetic enough to cleave many types of chemical bonds, most all of them, and they'll cleave homolytically. Each chlorine has an equal propensity to receive an electron. This is called homolytic cleavage, and it will produce for us 2 of these chlorine free radicals. So the free radical has an unpaired electron. Free radicals are extremely reactive. They'll react very quickly with just about anything. So both chlorine and methane are mixed together in a reactor, irradiated with UV light. They break apart. Carbon to hydrogen bonds are broken. Chlorine to chlorine bonds are broken. These free radicals randomly collide and form new hydrocarbons. We will get, in effect, a rainbow distribution of all the haloalkanes: chloromethane, dichloromethane, trichloromethane, and tetrachloromethane, and some HCl. This mixture must then be distilled to separate the various components for sale. A third important industrial reaction involving hydrocarbons is anaerobic, that means no oxygen, destructive heating. Again, this causes homolytic bond cleavage. We're going to heat up hydrocarbons in the absence of oxygen so they don't burn, provide enough heat, and we break chemical bonds. They will break rather randomly. So, for example, methane can be pyrolyzed in the presence of heat to methyl radicals and hydrogen radicals. Larger groups like ethane can producing ethyl radicals and hydrogen radicals. These radicals collide and randomly recombine, producing, again, a distribution of different hydrocarbons. In this example, we'll get some ethyl colliding with some methyl groups, producing propane. Why is this used? Well, about 95% of the petroleum that is processed is used to burn as fuels. Kind of sad. From a barrel of gasoline, only about 15% of the hydrocarbon in it is in a suitable molecular weight range to be used as fuel. Gasoline, diesel fuel, aviation fuel, only about 15%. So 85% of the barrel of gasoline is either too low in molecular weight or too high in molecular weight. So the barrel of gasoline is distilled. The 15% that's used for fuel is taken off. The 85% is put back into the distillation column after it's pyrolyzed or cracked. So by heating the hydrocarbons anaerobically, they will break and recombine, producing new mixtures of hydrocarbons, some of which will be in the boiling range required for fuels, and they'll be distilled off, and the remainder will be cycled back again. The process continues again and again until we get most of our petroleum in the molecular weight range required for fuels. Now, pyrolysis is also called thermal cracking, and when steam is added, it's called steam cracking. And there's more information on this in the text if you're interested. Sometimes pyrolysis is carried out in the presence of hydrogen, and that's called hydrocracking. Now, the reason for that is if we add some hydrogen and it breaks into radicals, they will tend to cap the ends of fractions of larger molecules that are broken off, and then we'll wind up with smaller portions. So here, 14 carbon hydrocarbon, tetradecane, and hydrogen can theoretically give us 2 molecules of heptane. This is called hydrocracking in the presence of a silica or aluminum catalyst, anaerobically in the presence of heat. And that's about all there is to tell about the reactions of alkanes. Page 68, Cycloalkanes. So cyclic alkanes are hydrocarbons with rings, and will have the general formula C to the N, H2N, where there's only one ring. Sometimes it's just written as CH2 taken N times, CH2 being a methylene group. Cyclic alkanes form regular polygons with equal bond angles. For expedience and simplicity, in drawing cyclic alkanes, hydrogens and carbons are not shown, but we mentally add the correct number of hydrogens to the diagram, knowing that carbon is tetravalent. It has 4 bonds in its neutral compound. So this is a correct rendering for cyclopropane, but more conveniently it's drawn as lines joined as a regular polygon. As a point of interest, the internal angles of a regular polyhedron are given by this formula, where n is the number of sides. So for example, if we have 3 sides, 3 minus 2 is 1, times 180 divided by 3 is 60 degrees. So cyclopropane has internal bond angles of 60 degrees. That's quite strained. What is the normal bond angle for a tetrahedral carbon? It's approximately 109.5, or we'll just say 110 degrees. If the ring is pulled very tight or stretched very far, it will be, in fact, more reactive than when the angles are close to the tetrahedral bond angle. In the case of cyclobutane, the angles are 90 degrees. If you work out the internal bond angles for the other examples, you'll find that cyclopentane has an internal bond angle of 108 degrees, which is very close to the 110 degree optimal, most relaxed arrangement. If cyclohexane and cycloheptane remained flat, they would have bond angles of 120 and 129 degrees respectively, but in fact they will pucker a bit to maintain a bond angle closer to 110 degrees. Let's learn how to name cycloalkanes. We add the prefix cyclo to the alkane name and combine this into one word without spaces or hyphens. When substituents are present, if the number of carbons in the ring is greater than or equal to the number of carbons in the substituent, then the compound is named as an alkyl substituted cycloalkane. For example, here we have 5 carbons in the ring, which is more than the carbons in the substituent, so it's named as an alkyl substituted cycloalkane, methyl cyclopentane. If, however, the number of carbons in the ring is less than the number of carbons in the substituent, the compound is named as a cycloalkyl substituted alkane. Here's a case where the number of carbons in the ring, 3, is less than the number of carbons in the alkyl substituent, and so technically this should be named as a cycloalkyl alkane, cyclopropyl butane. Now, having said that, I've seen many instances in literature where people have named this as N-butyl cyclopropane, and I'll give you the same latitude in this case. Now, for substituted cycloalkanes, we number each carbon in the ring sequentially. Counting can begin at any carbon and proceed in either direction. Then you compare alternate numbering schemes and choose the direction that gives the lowest number at the first point of difference. So for example, we have 2 methyls in this cyclohexane ring. We can number it 1, 2, 3 clockwise or 1, 2, 3 clockwise. In either case, it gives the same name, 1,3-dimethyl cyclohexane. What you should not do is go in a direction that gives larger set of locants. So this 1, 2, 3, 4, 5 dimethyl cyclohexane, that does not exist. And finally, when different numbering yields the same substituent numbers, we assign locants to substituents, numbering them by alphabetic priority. So here we have 1 bromo, 2 methyl, or is it 1 methyl, 2 bromo? Well, it's going to be 1 bromo, 2 methyl, cyclopentane using alphabetic priority. Page 69 is our last page in the study of alkanes. We're going to talk about stereochemistry, but before we get there, let's talk about some open chain alkanes. So acyclic open chain alkanes, well, they're free to rotate around single bonds. Different positions obtained by rotation around single bonds are called conformations. Can you visualize with me here? This represents a methyl group, CH3, and CH3, so this compound is in fact ethane. Picture the front carbon rotating relative to the back carbon. This particular representation or drawing that I have here is called a sawhorse representation, and it shows the hydrogens in the front carbon being exactly aligned with the hydrogens in the back carbon. We would say that this is eclipsed. If you lined these two carbons up exactly, the hydrogens in the front would block the view or eclipse the view of the hydrogens in the back, hence the name eclipsed conformation. Now, where does the term sawhorse come from? Well, this is a carpenter's sawhorse. It's used to lay a piece of wood on and cut it with a saw, and it looks similar in structure to this conformation, so someone called it a sawhorse representation. And again, this represents an eclipsed conformation. The carbon-to-carbon bond is free to rotate, so those hydrogens can all rotate in the front relative to the back. On the far right, we see, again, ethane. I'll draw some hydrogens in again. In this representation, in this conformation, we see the hydrogens in the front are exactly oppositely aligned with hydrogens in the back. This is called the staggered conformation. So there's the sawhorse representation showing the eclipsed and the staggered conformations. Again, this rotation can occur with minimal energy barrier. Usually at room temperature there's enough energy in the molecule for this to occur continually. On Blackboard I posted some hyperlinks to YouTube videos showing the rotation between various conformations, but I don't have liberty to put those in my video because they're not mine. Just check the links on Blackboard. Here's another representation that's used. This is called a Newman projection. The Newman projection on the left is equivalent to the sawhorse projection on the left. So the carbon in the front is represented by the small black dot in the front. The carbon in the back is represented by the large white circle in the back. The hydrogens in the front carbon are the ones that overlap the white circle. The hydrogens in the back are behind. And so this again is a eclipsed conformation, this time using a Newman projection, and over here we have a staggered conformation using a Newman projection. So here is a ball and stick model of ethane in an eclipsed conformation, and here it is in a stick model. And doesn't it look like a sawhorse projection? Here is a ball and stick model of ethane, this time in a staggered conformation, and again here a stick model, and again it looks a lot like the sawhorse projection. So that's open chain structures, various conformations. No bonds need to be broken to interchange conformations, just a small energy barrier. By comparison, cycloalkanes are inflexible. They allow very little rotation. The carbon-to-carbon single bonds, particularly in smaller rings, are held quite tightly. Even in larger rings, you can have minimal rotation. In order to really rotate the whole molecule, you'd have to break a bond. And thus, cycloalkanes have two different sides. They have a top and a bottom. And when they are disubstituted, meaning two replacements of hydrogen, a new kind of isomer occurs. It's called a stereoisomer. And take a look at these two molecules. You see they're very similar, but they're not exactly the same. Now both of these have a cyclopropane ring, and they have a chlorine on adjacent carbons, and they would be named 1,2-dichlorocyclopropane. But they're not exactly the same. These cannot be superimposed. Notice the structure on the left, the chlorines are on the top side of the ring, and on the structure on the right, the chlorines are on opposite sides of the ring. We need some way of distinguishing between them. We can't have two different compounds with the same name. So an additional prefix is added to distinguish between these two stereoisomers. When the two, and listen carefully to the words I'm saying, when the two larger priority atoms are on the same side, that's described as being cis. When the two larger priority atoms are on opposite sides, that's described as being trans. So when I say larger priority, I mean on the same carbon. Chlorine and hydrogen are on the same carbon. Of these two, which has higher priority? The one with higher atomic number, and that would be chlorine. On the carbon over here, again, the atom with higher atomic number is on top. It's got higher priority. The two higher atomic number groups are on the same side. That's cis. Here, the two higher priority groups are on opposite sides. Therefore, it's trans. Now, in the English language, you're probably familiar with the terms transatlantic. It means across the Atlantic, and here the higher priority groups are across or on opposite sides. There's also a word in the English language, cisatlantic, means on the same side. The prefixes cis and trans are lowercase and they're hyphenated, as seen. Now, you'll appreciate later that even cis and trans are limited in what they can explain, and you'll see there's an alternate system which is more inclusive, and I'll present it right here. The prefixes Z and E are also used, and they come from the German. Z stands for zusammen, and it means together, whereas E stands for entgegen. I'm not sure about my pronunciation, and that stands for opposite. So if you choose to use cis or trans, straightforward. If you choose to use Z or E, they're capitalized and they're in parentheses, where cis and trans are not. It's a small deduction if you get those confused. How will you remember that? Well, you can remember that cis means on the same side, and likewise Z means Z, same side. Even sounds German, doesn't it? Whereas trans or E is on the opposite side. Now, cis and trans isomers are a type of what's called a stereoisomer. They're isomers that have the same molecular connections, so they're more closely aligned than constitutional or structural isomers. Structural isomers have different connections, but these have the same connections. They're spatially or geometrically different, and so you'll also find them referred to as geometric isomers. They differ only in their geometry. Keep in mind that stereoisomer forms cannot be interchanged without breaking bonds. These are not conformations. They are actually different isomers. Let's get some practice. This is a cyclopentane ring, and I see substituents on the first and second carbon. When you're going to number the ring, we want the lowest set of locant numbers. So if I count this carbon forward as being 1, I'll have substituents 1, 1, 2. It would be wrong to call the one in the back 1, because then your substituents would be 1, 2, 2. We get the lowest set of locant numbers. So that's our numbering. We list them alphabetically. Let's go ahead and do that.
1 bromo, 1 chloro, 2 fluoro, cyclopentane.
But of course that's the same name as the one on the right here, but they are different. So to distinguish, we need to identify the stereochemistry. So on the same carbon, number 1 carbon, we have 2 substituents. Which one has higher priority? Bromine has higher atomic number than chlorine. On the second carbon, is fluorine or hydrogen have higher atomic number? Well, fluorine. When the higher atomic number, higher priority atoms are on opposite sides, this would be described as being trans
or E.
In the structure on the right, bromine is higher priority, fluorine is higher priority. They're on the same side. So this would have the very same name, except it would be
cis or Z.
I want to give you one more example here just to make sure you've got this. So how would you name this compound? For the lowest set of locants, we would number the carbons 1, 2. So I would name this as 1 bromo, 1, 2 dichloro, cyclopentane. Now, is it cis or trans? A lot of students will tell me this is cis, because you're not thinking correctly. We are not saying that the same atom is on the same side. We're saying which atoms have higher priority and how are they compared to each other. On the first carbon, bromine is higher priority than chlorine. On the second atom, chlorine is higher priority than bromine. So we have to describe this as being trans or E, because higher priority groups are on the opposite side. Again, it's not whether the same atom is on the same side. That would have very limited application, because oftentimes you'll have different substituents that are not the same. So don't think the same substituent, think which has higher priority. And that's pretty much it for the chapter on alkanes.